Okay, so our next up would be Kartik Anand from the Bank for International Settlements, BIS, and he will talk about filling in the blanks for interbank linkages and systems.
Well, thank you very much for still being here at the end of an engaging day. So this is joint work with Kartik Anand, who is here in the audience, and Ben Craig, who has just moved back to the Federal Reserve Bank of Cleveland, and myself. And the idea is quite simple and straightforward. Namely, interbank contagion is at the core of many systemic risk models, yet the bilateral linkages are often not observed. In such situations, the standard procedure is to estimate counterparty exposures by a technique called maximum entropy, which spreads as evenly as possible all the exposures across all your counterparties, all potential counterparties. However, that can be very misleading in several respects. If you're interested in the structure of the network, that's basically destroyed by this procedure because links are scattered everywhere. And if you're interested in systemic stress tests, it can also be misleading because there's an inbuilt assumption of diversification across all counterparties that you could reach, which is not like interbank networks are in reality. So this short paper proposes an opposite benchmark, which basically concentrates exposures as much as possible on as few links as possible, still consistent with the overall lending and borrowing of each bank in the interbank market. And we call that minimum density. It produces a highly concentrated and sparse network that looks much more like interbank markets in practice. It retains some of the original network characteristics, and it provides a useful robustness check on your systemic risk simulations. It is also wrong. It is also biased, just like maximum entropy is, but it's biased on the other side. So you kind of get, in a way, something like a confidence bound on your systemic stress test by using both benchmarks. So we're not saying this one is any better. We're just saying there's a structural alternative that you can also use. And we can basically check how close these two benchmarks are to reality because we do observe the German interbank network with all its bilateral linkages. So we can actually check how close these various benchmarks are and how they perform in a systemic stress test. So here is in one slide the idea. That's just a very simple example. Top left here is the actual interbank network, okay? With bilateral linkages, for instance, 2 is the amount that Bank E lends to Bank C, and 3 is the overall lending of Bank E to all other counterparties in the system, and 5 is the total borrowing of Bank C. So the rows are lending, the columns are borrowing, and this is the example matrix. Now what regulators or analysts or market participants for that matter usually see is this matrix. They do know from balance sheet information of individual banks their interbank assets and interbank liabilities. So they do know that Bank C borrows 5 from the interbank market and that Bank E lends 3 to the interbank market, but they don't know to who. And so it's very hard to track the path of contagion, of course. So what a practice has been so far is simply to use the maximum entropy solution to estimate the counterparty exposures. And that method basically spreads exposures as evenly as possible across all active counterparties. So here again, the example of Bank E lends to all other banks who borrow anything at all. If only D and E don't borrow in the interbank market, so the method places a 0 here. But otherwise, the matrix is basically complete. It's full of links.
So there is information of who lends to whom, but not the amount. That's what you're saying.
No,
No, usually what you see, the only thing you see is how much the banks lend in total or borrow in total from the interbank market, but they don't know with respect to who to who. That bilateral information is missing.
The maximum entropy, okay, you consider it because you know that D and E do not borrow at all. Okay, no,
yes, since they don't borrow at all, they don't borrow from anyone in particular either, right? So technically, it's just a matter of filling the blanks in this table from the marginals. Hence the title. So what we do is simply the opposite. We basically say, you know, how many links are really necessary at the minimum to replicate those marginals with as few exposures as possible. And the solution is this matrix. It's just an example, right? But you can see already that it tends to concentrate exposures somewhat more. Bank E, which lent 2 to C, in this version lends 3, which is exaggerated, but it's kind of closer to the original 2 than what maximum entropy has, which is much less here. So it tends to concentrate more exposure on fewer links, right? That's the basic idea.
That's maybe you should mention that. I mean, actually, this is also an extreme picture you have from the lower left panel, because usually you know a little bit more than that. You know, for instance, that on the main diagonal there are zeros because banks do not lend to themselves or borrow from themselves.
That's taken care of in the top
here. You know from the data sum of the entries,
yes.
And you can then even do maximum entropy estimation taking this additional information into account.
Yes.
It gives you a more realistic picture.
That's true. Now, the more you know, we have not programmed this way, but the more you know, you could in principle take out those links that you do know, adjust the marginals accordingly, and do this method on the rest of the matrix. So it's without loss of generality to just basically say we know nothing, right? Mm-hmm. In practice, it's right. The more you know, the better this method will perform. Right. As a result, of course, you wildly overestimate density and other characteristic network features when you use maximum entropy. Here, density was 33%. That is a third of all possible links are actually used in the original example. In maximum entropy, it could be up to 100% if all banks are actually active in the market. It will spread it to all banks. And what we found here is necessarily less than this. So it's biased as well, just on the other side. And now we're going to go into a little bit more detail. So the roadmap for this talk is very simply introducing the minimum density approach. In part 2, to basically compare these benchmarks to the true network in terms of network features. So just the pattern of exposures, the linkages. And in the third part, look at an application that takes the linkage pattern and the linkage size into account, running a systemic stress test. Okay, so let me introduce the relevant benchmarks first. So a couple of bullets on notation. So X here is the true network, which we observe in this case. It consists of bilateral exposures that are positive between banks, so I lending to J. The total interbank assets is one row of this matrix, and we observe that. And interbank liabilities is a column of this matrix. We observe that too. We call those the marginals, but we assume we observe nothing else. So maximum entropy comes in, if we use maximum entropy, we will simply spread the exposures as evenly as possible, subject to the marginals. Okay? Technically, it is you minimize the tile index or maximize the entropy, which is just the minus of that, subject to the entries adding to total lending by Bank A and the row adding up to total borrowing of Bank I for each I. Yeah? Simple enough. Now the advantage of this method is it's easy to implement. There's standard algorithms out there. It yields a unique solution for the estimated counterparty matrix. However, it has a couple of drawbacks. It is from an information theory point of view, it is optimal only if nothing else is known about a network. And we would argue that, well, we do know a couple of things about networks, and in particular, interbank networks, especially large interbank networks, are typically sparse. They are hierarchical in the sense that small banks often don't lend directly to each other, but through larger banks that intermediate between them. So there's really, that is just a hierarchical version of the sparsity, right? It's very much relationship based, and it has disassortative features. That means banks connect to each other that are unlike each other. So small banks tend to connect to larger banks rather than to other small banks. Because of course, larger banks are more likely to fulfill their business need without them having to go to various other banks. It's kind of more efficient to just connect.
All these features, you could include them through the price.
That's what I'm going to do. Well, you could include, but the prior in a maximum entropy thing would still not really place zeros. You could always, okay, you're saying you could structure more and more the maximum entropy approach so that it gives you zeros.
Say you put zeros between if you you sort into core and periphery banks, what you just said, you could place zeros on the periphery links.
But you have to figure out what is the periphery. Can you do that just based on the assets total?
Well, if that's what you want to put in, if that's an information you have.
You could do it in the constraint.
Yeah.
Well, you could, what is true about all these comments is that you could structure your maximum entropy approach by using additional information in a somewhat loose way, but you could do that. You could say, I assume that those banks are too small to connect to each other, so I just pose zeros there, and I do maximum entropy and all the rest. Our approach has been just to come from the other side and to say, what if we do the logical opposite of maximum entropy? What do we get, right? So clearly built in the idea of maximum entropy is a diversification assumption. I'm dealing with everybody else that's active in the market. So that's a strong sense in which there is diversification, which is kind of stronger than what you see in actual interbank networks. And as a result, you typically get that entropy-derived matrices tend to underestimate systemic risk. That's a known problem, but there hasn't really been much of a solution to that. Now, ours is just an alternative benchmark. It's part of a solution, but there could certainly be others. So what we do is that we start from the premise that network linkages are costly to maintain and are based on relationships. It is simply not true that banks lend to everybody else in the system. It would be, especially for small banks, it would be way too costly to do credit worthiness checks on thousands of counterparties, and the information processing and the risk management would just be prohibitive. At most, the very large banks are going to do that. So what we look for here is an efficient solution in the sense that we're looking for minimally connected networks that satisfy the marginals. So let me state the problem. It's easy to state. It's a little harder to solve. This simply minimizes the number of connections. That's like a fixed cost of making a connection overall. So that's like a planner's problem. Not an individual bank's problem, but a planner's problem. Subject to the positions you put in have to add up to these marginals, as I've mentioned before. Now, the economic nature of this problem shares some common features with transportation, right? Because in a way, moving goods from n destinations, from n origins to n destinations is kind of analogous to the problem of moving money from n banks to n other banks. And these kind of problems, network design problems in transportation, are generally NP hard. That means really difficult to solve exactly. But they also involve typically the presence of hubs, like a certain amount of central locations that serve as kind of intermediaries where you don't want to build bilateral roads through to all the between all the locations. You want to go through kind of transportation hubs, right? And we will find a solution that's kind of similar to that in nature. So our approach is guided by two main ideas. First of all, we try to solve this with an algorithm because an exact solution is just impossible to find when you're looking at a system that's as large as the one we look at, because we have 2,000 banks. The number of possible combinations is exponential, and even before you allocate values to the individual links. So we have to resort to an algorithm. And there we basically use two ideas. First is the link prediction, and the second is loading the link. Okay? The first link prediction works as follows. Here we just draw on some results from information theory, which basically says choice under uncertainty, it is optimal to attach probabilities to individual options, right, that are proportional to a prior times to the value to the value of the problem that adding this link creates. Okay, so we've called the value of our problem V, right? If you add that link and you load it, how much does it add to the value of the problem? If it adds a lot, you wanna add that link. You wanna choose that particular linkage. That's one idea. So that can be done optimally with a multinomial logic function. And then we build in the economic incentives through the priors. So basically we say, well, what makes it more likely that a link exists? Well, here comes back this idea that relationships are often disassociative. So small banks tend to link to large banks. The way we put this in here is, these are deviations from my, you see this is going to be an iterative algorithm. So I keep on allocating value, right, as I proceed through the algorithm. And so if a bank still has a lot of assets to allocate, and another bank has very little liabilities to obtain, meaning money to borrow, then we want to match those two. So the probability of a match is going to be higher when it involves a large bank lending and a small bank borrowing, or a large bank borrowing and a small bank lending. This basically just says you tend to match unequal banks with each other. And the logic is simply this. It's efficient. When you're a small bank, you don't want to go to 12 other banks to cover your needs. You just go to one big bank, and you know that bank is big enough, it can just lend you the money. It's not difficult. If you tried all these small banks instead, you'd have to go to 10 or 20 small banks until you've got the funds together. So that's kind of the economic logic there. So all the algorithm does really is to identify which links are most likely and then to load them with the largest amount consistent with the marginals. So this is how it works. Iteratively, you compute the current amount that still needs to be allocated on the asset side and on the liability side. Then you select a link according to the probabilities, as I've detailed before. You load the exposures with the minimum between what is the current assets to lend and the current liabilities that still need to be contracted. So if bank I needs to lend 5 and bank J still needs to borrow 10, you can allocate 5. Yeah, that's the minimum between them. And here we introduce a lambda that usually we set 1. But it's a parameter that allows you to soften the problem somewhat. So if you set lambda equals 1, you get the minimum density network that has the absolute minimum number of connections. That's kind of the lower bound. If you allow that allocation to proceed, at least for a while, with a lambda less than 1, you're not allocating as aggressively as you can, and you allow the solution to have more links than the absolute minimum. So this way you can kind of soften the problem a bit, and you can get solutions that are not quite as aggressive and extreme as the minimum density solution. And that allows you also to do a bit more robustness on your systemic stress tests. So basically, you then update the set of priors, and you just repeat this until the whole overall volume of the interbank market from the marginals is all allocated. Yeah. And in practice, we use a system with 2,000 banks. We always manage to find solutions that allocate 100%, and where these marginals are fully respected, just like with the maximum entropy solution. So this is not a thing that just doesn't converge or so. Yes?
I think you could probably achieve this by using a transportation algorithm, couldn't you? Because the point of the transportation algorithm is that you've got sources and destinations and costs on the links. Now, I mean, in this situation, you don't want the source to send stuff to itself, so you put huge costs down the diagonal. Off the diagonal, it's really not terribly important what cost you put in. And then the transportation algorithm is a special case of the linear program. It delivers you a basic feasible solution, which gives you the smallest possible number of non-zero values in the solution Z. And it's blisteringly fast.
Good. Then I'd love to hear more about it.
Yeah.
So this would be, although this has, relative to the normal transportation problem, which I'm not all that familiar with, but it does have 2 capacity constraints on every node, right? So it's going to be pretty involved nonetheless, right? Because
So
the
the capacity constraints are these A's and the A and the
yes,
L.
yes.
No, that's standard transportation algorithm.
It is?
Yeah.
Well, this one is reasonably fast as well, but I mean, it would be good to try various algorithms.
talk about it after.
Yes, I'd love to. Yes.
That would always also have the advantage that you could build in quite painlessly some prior knowledge of the structure of the network, because not all large banks are equally accessible to all small banks. They may prefer to deal with Eurozone rather than, say, ICBC or something like that.
Absolutely. And this would be, we've done a very parsimonious approach here by just using the information in the marginals. But you're absolutely right. A more general approach would basically run a probit, where you can put in any information that appears useful, like the size of banks, any balance sheet information that you might otherwise also have, whether they're the same business model, whether they're in the same location or geographic area, etc. So you can condition this in many other ways. We've just chosen the way with the least, that requires the least information, but you could certainly expand on that. So, let me get to the empirical part. So this, we do observe the actual network that we're trying to reconstruct here, right? So we can do the horse race kind of thing. And that is the German interbank network between about 2,000 banks on a consolidated basis. It's a pretty big network. The exposures are well over 1 trillion, and basically the sparsity is such that only 0.6% of possible linkages are actually used. It does have a core periphery structure whereby the periphery banks do not lend to each other directly, but almost always go through one of the very few, about 40 core banks. Now, the maximum entropy solution, of course, blurs that network completely. It has a density of 93% because most banks in the German interbank market happen to be borrowing and lending at the same time, even if it is small amounts. But that basically means they're all active on both sides of the balance sheet, so you're basically proliferating linkages everywhere, and the structure is basically lost. The minimum density solution is kind of too efficient in that it only needs 0.1%, that is 6 times less links than are actually observed to allocate the same amounts.
But here you look at the density, which is zeros and ones. But maybe a better way to look at it is the distribution of the weights. Because if you get the tail right, maybe that's okay.
I think that's what this shows. Correct me if I'm wrong, but this is, on the x-axis, is basically the links ordered by size in the original network. So here are the biggest links, and here is 100% of, by the time we are here, we've covered all the links in the original network, ordered by size. And here you see how much value is allocated by the time we get to the nth link. So by the black line is the original network. Once you've covered 100% of the links in the original network, you've allocated 100% of the value. Obviously, that's simply the original network. The minimum density approach allocates much more aggressively. So the n largest links are going to be even larger because you're loading them as much as you can. Because, of course, you want to economize on the number of links, so you load each link as much as you can. And by the time you're on about at not even 20% of the original number of links, that is a sixth of the original number of links, you're already done with allocating. Yeah? Then all of the interbank volume is already allocated. Whereas the maximum entropy solution, of course, takes forever. It takes like 150 times longer than, this would only converge to 1 by the time, we're in Cambridge or somewhere.
Yeah, but on the left, it seems that the maximum entropy gets it right.
Yes.
The big exposure.
That is because the prior in a maximum entropy is basically my size times your size. Mm-hmm. So it also allocates big amounts to the big counterparties. Yes, we're not saying the maximum entropy solution is useless in that respect. I mean, it has many good uses. This is just to show where the differences come from between the benchmarks, and in particular that our approach concentrates the value of the links much more on fewer links. So here we just compare some of the structural features in the network. If you just look at the pattern of linkages, in blue, here you have the typical network measures, some of them, and here you have the true network, which we observe, right? As I said before, the density is about 0.6%. In maximum entropy, obviously, it's hopelessly, it's almost 100%. It's way too high. Our solution is way too low. Same for the average degree, of course, and for the median degree as well. So in the true network, the typical bank has 6 connections. Here, the typical bank has just 1 connection because it's been designed like that if you can satisfy your funding needs with just one bank, that's what the solution is going to give you. So only the largest banks have more than one link. Now, one feature that is of course going to be in our solution as well as in the true network is the negative associativity. That means unlike banks tend to be linked to each other. In this case, defined here as the correlation between the number of links of two banks that are linked with each other, so that this simply means less connected banks are more likely to be linked to more connected banks. And that feature is preserved in our solution, and it is not in maximum entropy. Now here is another indicator, dependence when borrowing. It's not a standard indicator, but it basically just says if I need to satisfy all my borrowing, how much of that depends on just one counterparty, on my largest counterparty. And in truth, it is the typical bank relies on its largest counterparty 84% of its total funding. And in our solutions, of course, even more. And in maximum entropy, it's much less because you're borrowing effectively from everybody. And then a couple of other network features are also compared here. I'd like to just point out that the one where our solution really does poorly is on clustering. That's basically the probability of two of my neighbors to be themselves connected. Our algorithm does really poorly there because there's no need for these other guys to be connected, right? It's enough if you have this link and that link. So that's by design in a way that you get this result. Yes, question?
So I was wondering, if I understood it correctly, your algorithm doesn't create a unique network because it's probabilistic in a way. So should I understand it as a result of Monte Carlo simulation for the minimum density, or how did you get this one particular?
That's a good point. So you can have different philosophical approaches about that. In a conceptual way, you might think that a minimum density network might be a unique thing, where there is always, if I run 1,000 of those, I will take the least connected one and say this is the solution. But of course, since we have an approximation algorithm, it has a stochastic element to it. So each time you run it, it will give you a slightly different solution. But in practice, we've run hundreds of those, or even thousands, and you always get within a very narrow range. So narrow, in fact, that I didn't want to bother writing the plus-minus standard deviation here because it's tiny. It's very small. But in practice, it's true because each solution places the big links potentially slightly differently. So you could have different contagion implications for each of those networks. Now, you could see that as a disadvantage, or you could see it as a strength in that it allows you to do robustness. You could do this 1,000 times, and you would get a better feel about what the systemic risk properties really are, because you have a range of outcomes. Okay, so these slides I just race over in the interest of time, because all they say is that maximum entropy, this is a degree distribution, maximum entropy obviously does very poorly compared to the true network, and our solution is below that, but at least it kind of retains the shape somewhat. And this slide, you can go to details, to the paper for details. This basically just says I can vary this parameter here and get different solutions that are not quite as aggressive as the minimum density solution. And so I can try to get with some of these network features somewhat closer to the true network. But there's many ways in which one can do that. So we didn't really pursue that systematically here, because to do this intelligently, you would need to know more about the original network that the users of this code might not know. So there's many ways to do it. It's not clear what the best way to do it, but this is just to show it gives you the option to experiment with these solutions and to use them in some robust systemic risk assessment. All right, now to part 3, last part. How does this perform in a systemic stress test? And clearly for a systemic stress test, not just the pattern of linkages matters, but also the size of linkages, right? And there it's not at all obvious that what we add here is any better than maximum entropy. So now here we're taking a totally standard approach to stress testing because we don't try to innovate on the stress testing part, but what we try to innovate on is the inputs to stress testing, namely the different matrices, right? So we take a standard stress test and compare the results that you get from these benchmarks, maximum entropy and minimum density, to the results that you get from the true network. Now the standard methodology has the 2 ingredients. First, a trigger of contagion. That's simply a single bank failure plus a capital shock of 2% of core tier 1 capital. That basically just is a shortcut way of saying what if asset prices drop and all banks in the system see their capital ratio fall a little bit. Okay, so that's basically just to mimic an aggregate shock. Then we compare 2 mechanisms. The first one is the sequential default algorithm that has been used for a long time, at least since Verfine, in these kind of exercises. And second, the Eisenberg-No clearing vector, which is internally consistent in a way that the first is not. So we sort of prefer that one. So the method is always the same. You just let one of these 1,800 banks fail, and you study the cascade. Who fails next? You know, does that have further contagious effects? And then you measure how much system assets are affected. What are the assets of the defaulting banks? What is the total deadweight loss? And then you do this for all the 1,800 banks, and you report the average over the defaulting banks, right? So 1,800 single failures, the consequences, and then you just average over the results. And then, of course, what we want to do is to evaluate how close are these benchmarks to the true network.
So over what do you average?
So you have 1,800 simulation results in each run, and you average over the banks that initially fail. So you let each bank fail once, and you measure what the consequences are.
So you have a very heterogeneous system in which you have a few systemic banks.
Mm-hmm.
Most of the banks are not systemic. They will not
Exactly.
create contagion.
Yep.
So you're averaging a few big numbers with
Absolutely.
99% of 0.
Yeah, but of course we have the original results, right? We can show other. So I'll get back to your point in a moment. Have a look first at contagious defaults. This is for the sequential default algorithm. The black line is sort of the truth, right? The truth. That's how contagion is when you have the true network, right? So we treat this as if it were the truth, right? And then we look, where do we find, what does the minimum density, how does that relate, how far is that from the truth, and how far is the maximum entropy solution from the truth? So here you have the number of banks that fail, excluding the first bank, on average, the system assets affected in billions, and the deadweight loss. Now, and here you have loss given default. That's kind of a measure of bankruptcy cost. So clearly the greater bankruptcy cost for every single failure, the more failures you have overall, because there's less recovery of the defaulted debt. Now, on your point, here, for instance, here, you see that if you have a loss given default of 40%, the average number of banks that fail is just 2. But of course, if you condition on, I mean, most banks do not induce any default, any further defaults. Now, if you condition on that that contagion takes place, you get an average of something like 50 to 100 here. And if you take the biggest bank in the system, 1,200 banks fail. So it's a huge distribution, of course. And there's probably better ways to summarize the information, more informative ways. What we've chosen here is to use basically the format that Mistrulli and other typical studies have used, because we don't really want to innovate on the method of measuring contagion. We want to innovate on how to find an appropriate matrix to put into that exercise.
I just make that point because this is what's always reported in these papers, and then people look at this and say, "Oh, contagion is negligible because 1, 2."
You're right.
But actually, if you look conditionally, it's
Nothing to do with Lehman.
yeah.
Yes, exactly. Well, that's a good point, and we do discuss that a little bit in the paper, but it probably warrants a bit more attention. Yeah. Okay, so what you can see on the whole is that on the number of banks, this is kind of the true contagion. The red is the contagion estimates you get when you put in the minimum density solution, and the green one is the maximum entropy solution. So you can see that the maximum entropy solution underestimates the extent of contagion systematically. Ours overestimates it systematically. You don't see that here so much, but you see it a little better here. But it's not 100% clean in that we are not always above the true. Here you can see a little area where the true is even higher than what we obtain. But on the whole, you get the impression that you can get a useful range here. Our approach does not necessarily do better than maximum entropy. And in some applications, it will do worse. But it is good to have another extreme, another benchmark, so that you can kind of bracket the output from these systemic risk exercises somewhat better, because you have to remember that the black line, you do not see the black line. Most regulators in the world cannot run the true kind of contagion pattern, that's the black line. And so they just need to resort to some benchmark. And what we're saying is, here is a structured alternative that gives you that errors on the other side. And so you get a range of outcomes where you can be pretty confident that the true extent of contagion is kind of bracketed in there. We basically get the same results if you change the methodology, switching to Eisenberg-Noy. The first methodology is, in our minds, somewhat flawed because the sequential algorithm does not recognize that when you go on in contagion and there's more and more banks failing, then the loss given default of the first set of banks gets worse and worse and worse. It does not recognize that. But the clearing vector methodology does this as a simultaneous problem, and so they get that right. And here you get basically the same pattern. The true extent of contagion is bracketed between the maximum entropy and the minimum density outcomes. So the interpretation of the results are pretty similar across the different methodologies of contagion methodologies, but they are quite different across the input networks, right? The networks you put in, the true network or minimum density and maximum entropy. So maximum entropy in our estimations always underestimates systemic stress quite substantially. That is because it assumes that all banks have very diversified portfolios, when in reality they do not. And because they're diversified, each individual failure of a bank is distributed to many, many other banks. Small losses, they can handle it. The minimum density, our approach, overstates contagion because it concentrates exposures on few links, and these links are larger as a result. So if your counterparty fails and you're the only one, you know, that's your only counterparty, you take a big hit. Now, so there's kind of two countervailing effects. One is that the exposures are larger, so that tends to produce more contagion. On the other hand, there's fewer conduits. The minimum density matrix is quite sparse, so there's fewer kind of opportunities for contagion. But it turns out that this effect dominates because of the negative assortativity. And that is because a lot of small banks are affected by the default of a large bank because they have concentrated exposures. And so that's what drives the result. So the finding that the maximum entropy solution tends to underestimate contagion basically confirms some of the results in Mistrulli. And we find it holds also across different contagion methodologies, but we do not find a tipping point where there is some level of loss given default where maximum entropy, actually the diversification in the system, causes more rather than less contagion. In our simulations, it always causes less contagion. So I'm out of time, so let me conclude. This paper just had a very simple goal, which is to provide an alternative benchmark for estimating counterparty exposures. It does so by using some elements of information theory and some economic rationale to fill in the missing blanks. And the solution retains some of the original features of the true matrix. And in stress testing applications, it tends to overstate contagion, which is also a bias, but it's a bias that goes in the opposite direction of the current benchmark. And so hopefully the use of both benchmarks together help you bracket the results in a way where you can be pretty sure that the true extent of contagion is somewhere in between those extremes. So clearly this kind of research shows that the marginals have been the same in all of these networks. So the broad message would be that the pattern of linkages, even for the same amount of overall borrowing and lending by every single bank, matters greatly for systemic risk. You get quite different stress test outcomes depending on which solution you're going for. So thank you very much.
I like this idea very much, that saying that making links is costly, and then look at it through a transportation problem to get this extreme minimal density matrix. The only thing I did not like so much is that I think you're not being very fair to the maximum entropy, because you're giving really a caricature version of it where you only know the marginals. But I mean, in fact, in the maximum entropy you could take a priori information into account via the prior and via the constraints. So it's a convex.
What constraints?
You can say, like, for certain cells in the matrix, I know, for instance, the exposure is greater than this number, smaller than this, or it's 0, or other kinds of everything you can pack into a convex constraint set. So maybe it might be a good idea to, if you can run additional simulation showing that if you do maximum entropy with taking more prior information into account, will this range between minimum density and maximum entropy shrink? Or,
Yeah.
It might be interesting.
It should almost definitely shrink, right? Otherwise, someone screwed up some code, right? Because
Oh no, I mean it can expand the difference. Depends what kind of information you put in.
Yeah, sure.
If the information is
well, but if the information is true, it should get the maximum entropy as well as the minimum density closer to the original. But of course, is this approach linear and well behaved? Actually, that's not clear. That's true. Now, of course, I'm aware that you have used maximum entropy in this structured way in your own studies, and the more you know about, the more you have additional information, the more precise that method becomes. That's clear. I think the same would hold for our method, and as you would predict, it would probably narrow the range. So I'm not trying to bash maximum entropy as a method overall. I'm just saying here's a logical opposite that we can also use. Right.
Yeah, little similar remark. Also, one point is if one puts the information which you also use that big big banks connect with, you could put this information in a prior also, and then you get the generalized maximum entropies solution. It is known that this solution, maximum entropy, adapts quite a lot to the space points of low probability. So if you give low probability to some connections, then this will appear also in the maximum entropy solution. But the other way would also be, as Chris said before, you could here in this transportation approach, you give just the same cost for all connections, but you could also make there the difference and put the prior information in this cost structure. And I think the solution with his simplex algorithm is quite fast and can handle easily 1,000 or more variables. And so also there one could put more somehow structure or more information in the cost function, and then
yeah. Well, certainly this is not. We have not exhausted the possibilities.
So this would be one extreme case with
Yes.
the same cost for everything, but you could put more information and then maybe get solutions.
Sure. Yeah. Yeah.
So I think to say first, let me add one more comment on the sort of maximum entropy thing. One important issue is how to choose the kind of gauge to measure the performance of the maximum entropy and the minimum density. So basically, in your kind of presentation, you measure those two algorithms' performance by unweighted matrix data, isn't it? So density, degree, associabilities, and clustering coefficients, and others, all unweighted degrees. So, but in reality, in the financial network, so basically, say if we have the linkage of the 1 pound, this is all basically the same as 0 pound, isn't it? So critical difference is whether we have huge linkage with 100 million pounds or not. So in unweighted networks, there is a world of difference between 0 and 1 pound. But what we are interested in is whether they are large exposure or not. That matters most when we study some kind of contagion models.
Yeah.
So that's what I think that maybe it would be better to just check some sort of a correlation of the weighted matrix. As for example, Pearson correlation, as you should use in a different paper. So basically, previously I have kind of tested the maximum entropy estimated network and the actual UK interbank network. Actually, the Pearson correlation coefficient is quite high because basically you said that maximum entropy distributes the exposure equally, but in reality, basically larger banks have the bigger exposure.
Of course,
that's the kind of maximum entropy. So it has some sort of the core periphery structure by itself.
So, okay, you're making kind of two related points. One is to say, here we need to also evaluate with valued, metrics that take the valued nature of networks into account. And sort of the dependence does that, but not the others. That's true. One could add.
You have it in the graph, in the plot.
Yeah. Well, one could add some of these measures. Granted, that'd be interesting. The second point you made actually goes to a deeper question. When is it appropriate to use basically maximum entropy? And if you're looking at a small system in the UK, you only have information on the top banks. You don't have them. You don't have them on the whole system and on the smallest banks and on their interconnection. So when you look at only the largest banks and their connections to each other, maximum entropy does reasonably well because they're actually all connected among each other, right? And so the entropy thing says basically their exposures are proportional to their respective sizes, right? The product of their sizes. That's probably a fair description. And in fact, the solutions would probably not our solution might do worse in that kind of context. It does better in a very sparse context. I'm also working on international banking statistics between countries, and the aggregation you have in this kind of data, I would rather use maximum entropy than this method. So it's a question of, where do you want to, when is it appropriate, and if you just want to play safe, you could just use both and see what the differences are.
And basically say, Steve, sorry, can I add one more? Sorry, just quickly. So basically saying, you kind of say you focus on the existence of the connections, or the density, or the number of degrees, the number of nodes or degrees. So, but I'm not quite sure that is a really right measure to think about systemic risk or interconnectedness, because it is true that when we think about the Eisenberg node type or the fine sequential algorithm type algorithm, more node is less risky because the counterparty risk is diversified. But this is correct only when we have some kind of binary kind of default model. If the kind of loss, counterparty loss is bigger than the capital, and then that bank suddenly goes bankrupt, and then all loss spread further. But if the loss is smaller than the capital buffer, then nothing happens in the model. So, but in reality, if the kind of say counterparty loss consumed 80% of the bank's capital, it should have some further impact, even if the bank still sold them.
Sure, but so what in practice would you minimize then? I mean, let me first say that the purpose here, or the contribution of this approach, is not really, is quite independent of how it does in a systemic risk exercise. So the purpose is not to get to a matrix that does the best in a systemic stress exercise. Instead, the purpose is to say, how can I construct an unknown interbank network in a way that is the opposite, the logical opposite to the maximum entropy approach. And then we look into, okay, what, does it do well on structural features? Does it do well on systemic risk measures? And we could add like 10 other things. Does it do well on this or on that, or right? So it's not geared towards systemic risk assessment. It can be used in it if but it's not necessarily geared towards it. But if it were geared towards it, what would you put in? What would you minimize rather than the number of linkages? Do you have something in mind?
Yeah, so basically say, I think, okay, not the right measure right now, but yeah, okay, later.
We can maybe take this to the...
So let's move to Torben and then we can continue.
So this is also spurred by the observation that for many applications the tails might be the more interesting of the really big linkages, and it actually seemed like the maximum entropy did a little bit better on that. So I wondered if you could take for some of the very large linkages, you could use maximum entropy, then lock those in, and then go to the other algorithm and fill in the rest, because you did dramatically better after that.
Yep.
Now that might have been an artifact of your well, you actually had the data, so it was an artifact of your particular sample perhaps, but it was
That's an interesting
pretty
point.
compelling. But then you could kind of smooth between one and the other.
You could
Right?
certainly...
You get the tail kind of right, and then you get this big, quicker ascent to the right 100%.
Yes, there is...
And so
there is-
put that into the simulation and see.
Right. There's many ways in which we can deviate from that. And actually, we've tried one kind of related thing earlier on, which, if you remember, this slide, the prior, we've played around with another prior, and in particular, we've played around with a prior that looks like maximum entropy, multiplying this times that. So in a way, then it's proportional to your size times my size, and that's the prior of the size of the link. That gives us way more contagion, in particular because the large exposures are huge, right? The exposures between the large players are huge. But then we found that somewhat less useful because it didn't. We found that this specification is much more efficient because it knocks out all the small banks in one go, because every small bank can just connect to one large bank and for all of its business. And we think that's fairly realistic. You saying now we can mix both. Yeah, that's an interesting idea. One could do that.
The
Sure.
second point is on Rama's. We had these graphs where it was averaged over the 1,800 banks. It would be great to just see them average over the 30 largest or something like that.
Yeah.
That's what we if it is for systemic risk assessment, those are the only ones we think of as
Yeah, but in
systemic
that
risk.
case, you might get the opposite conclusion.
And that's important. Check.
Yes?
Details look better than the other.
Yeah, that's a good point. Yeah, we do not know. Yes,
Exactly. Could switch.
great.
Thank you very much.
Thank you very much.